Right, so for this section, we're going to be talking about how the nuclear reactor works. How do we actually get energy from nuclear reactions? Goals for this section, you have to know how nuclear theory works, so what's actually going on inside of a power plant or a bomb that makes it release energy. You have to know how we use that energy to make electricity, and you have to know a little bit about how nuclear power plants and coal power plants, um, how they compare. Right, so how much energy or how much material do we need to fuel one nuclear power plant and one coal power plant? How much electricity does it generate and how much waste does it generate? Right, because we're looking at nuclear as an alternative to fossil fuels, but if nuclear ends up being not better than coal, then it's not worth it to do it, right? So it's always important to think about what our alternatives are. And if it's not a good alternative, well, don't use it. So first thing is talking about how mass and energy are related. So if you remember E equals mc squared, that is the famous equation from Einstein that connects mass and energy, right? So if you multiply a certain amount of mass by the speed of light, that's how much energy you're going to get out of it. And the speed of light is a huge number, right? And that means that there's going to be a lot of energy and matter in mass. So very little amount of mass can produce a lot of energy. And we see that with nuclear reactors, right? So there are two general ways that we go about using nuclear energy, right? The first style or flavor is going to be nuclear fission. So the word fission is like a fissure, it's like a splitting of something. What is that something? That something is an atom. So atoms normally don't break apart, right? They may trade some things like electrons, they might lose some stuff naturally through radiation, but when humans first discovered that, hey, we could intentionally split atoms, the result of that was a huge release in energy. The second kind is a fusion, and that's exactly what it sounds like. Fusion fuses atoms together, and that's really cool. It's because it's counterintuitive. So in chemistry, you learn how when bonds are formed, it takes energy. When bonds are broken, it releases it. But the atoms don't necessarily play by the same game, right? So both breaking atoms apart and bringing them together can release energy, a lot of energy, right? 1 kilogram to 2.5 pounds of material that is nuclear is what it takes to make a nuclear bomb. And we know how devastating those can be. Just 1 kilogram. That's not much at all. Imagine 1,000 or 1,000,000 kilograms. It's very, 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 very powerful. So here is a diagram where you can just look at it. So the fusion is when two things come together, and fission is when a bigger atom splits apart. Now, the fuel for nuclear power plants is going to be this element called uranium. So it's really cool, like Uranus. Now, uranium has different isotopes, which if you remember is having a different amount of neutrons but the same amount of protons. So the two isotopes I need to know are uranium-235 and uranium-238. Now, in any nuclear power plant or nuclear bomb, there's going to be a mixture of those two isotopes. For nuclear power plants, we only want something like 4% of uranium-235. For nuclear bombs, it's much higher, but the ratio is pretty low if we're just talking about nuclear power plants. So if you remember in section 1, we were talking about the differences between a power plant and a nuclear bomb. Well, a nuclear bomb has a much higher enriched level of uranium. Well, what does that enrichment mean? Well, enrichment is the process of separating uranium-235 from uranium-238. Now, why would you want to do that? Well, uranium-238 is the type of uranium that can go through fission. Uranium-238 cannot. So sorry, 235 can go through fission, but not 238. And based on the reaction mixture, you can make a controllable chain reaction that can release a lot of energy, and the energy can be used to boil water, turbine, steam, all that stuff. Now, the general idea of what I want you to think about is as a chain reaction. So as you can see right here in the video, the guy has a little tiny domino, and a little tiny domino can hit and knock down a smaller domino. and then a bigger domino, and a bigger, and a bigger, and a bigger, until a giant domino that would not have been knocked down from the first one gets knocked down. So nuclear energy works a lot like that, where one reaction can cause a bigger one, can cause a bigger one, can cause a bigger one. And eventually you can get a really big explosion like this one. And again, nuclear power plants aren't nuclear bombs. They're not going to do something like this, but this is the ultimate potential, right? It is that powerful. It does create a ton of energy. Now, we don't want that big explosion, so how do we prevent that? So it's not an uncontained reaction. The whole point of the nuclear power plant is to contain reaction in such a way that we get a lot of energy from it, but not so much that we actually accidentally blow up the power plant. How do we do that? You have 4% uranium-235 and 96% uranium-238, right? A particle was going to strike the first uranium, and then more uranium atoms are placed in such a way that in space, the breaking apart of the atoms are going to hit like bullets, the next one and the next one and the next one, just like those dominoes in the video before. Now, sometimes what that does is generate this other atom called plutonium, and nuclear is considered a renewable resource because of this reaction. So within one kind of goal of splitting uranium to get the energy from it, you've actually been doing fission, where you split the uranium, and fusion, where you generate something new, in this case, a plutonium. And that's really important because plutonium has a lot of energy in it too. We can actually use plutonium as a nuclear fuel. So by using nuclear, we make more nuclear fuel, which is directly the opposite of fossil fuels, right? When we use fossil fuels, they're gone, they're blown up, we can't get them back. But when you use nuclear power, it generates more nuclear fuel, so you can keep making more nuclear power. So I thought that was really cool, really neat, because nothing else is really like that, where a substance is destroyed but created at the same time and is still usable. Now, the nuclear reactor is a combination of a couple of different components. So there is the moderator, and the moderator helps to moderate things. So what's the point of that? The moderator stops the reaction from going too fast or too slow. Both those situations are bad, because if it goes too slow, then the reaction dies, and it's really hard to get it back and generated and started again, and you don't want that. You want continuous power supply. Worse though is when the reaction is too fast and there are too many reactions going on. That releases a lot of energy, and that can lead to very, very big explosions, which is not good at all. Now, what can cause that is the fuel rod. So it is an actual rod that is placed within this kind of canister, and you put the fuel rod down into the canister with the moderator. But what is the fuel made out of? Well, it's made out of nuclear material like uranium-235 or plutonium, and you're going to intentionally break apart those atoms in such a way that they break apart the other atoms, which then break apart the other atoms, and then the other atoms. Now, the other part of that is going to be control rods, right? Now, control rods, they absorb neutrons. Neutrons are the things that fly off of the fissible material, right? They're the things that keep the reaction going, and you can use those to control the reaction. The more control rods, the more absorbed neutrons and the less reactions, right? So here in this diagram, we have a schematic of how the control rods and nuclear reactor work. In purple, we have the moderator of graphite, so that's going to be absorbing lots of the heat. The fuel elements will be something like uranium or plutonium, and the green is the neutron absorber, so that's going to be our control rod right here. Because we don't want too many reactions going off, but we don't want too few. And the way we control that is based off the depth of the rod in the reactor, right? And when it's all the way out, there's no reaction going on. It can't do anything. But as you go farther down, it's going to increase in power, because you're going to be facilitating more and more reactions. And this water here, its job is to absorb all that heat as well as some neutrons and heat up. And of course, when we heat water, it makes steam. Now there are more advanced reactors that don't directly convert into steam. We'll learn about that later, but in any case, there's always some kind of heat absorbing element which is used to make steam later on. So basically, you have the nuclear fuel. It goes through some kind of fission or fusion based on how much energy and how much steam is needed. The more you do the reactions, the more heat it generates and the more power you can consume. Now, we can put that water under pressure, which is really neat because at standard atmospheric pressures, water is going to boil at 212 degrees Fahrenheit. But what's really smart about these nuclear reactors is they take advantage of the physics and they increase the pressure. And that's also going to increase the boiling point. And you can get water all the way up to 600 degrees Fahrenheit and it won't boil. Okay, so why would you want to do that? Well, it's to keep the water contained that is in contact with the nuclear radiation. You don't want to turn that water into steam and then spread nuclear radiation all over the place. So instead, what happens is the water is put under pressure, it's superheated to 600 degrees Fahrenheit, and then placed through like a tube, steel tube. The tube is also going to get very hot because, as we know, metal is a very good conductor of heat, and that heat from the water inside the tube is actually inside like a bigger pool of water that never touches the nuclear material, so it doesn't have any of that radiation in there. And from that water is what the generator uses to make steam. Now, sometimes there is a problem, like we talked about yesterday, where for whatever reason, cooling is lost. And that's a very bad situation. It got an acronym, right? It's called a LOCA, right? Which is fun because it also means crazy, right? And it's a very crazy event where you lose cooling. So it literally stands for a loss of cooling accident. And that's very bad. If you lose cooling, then what happens is those fuel rods in the nuclear reactor go crazy. They do lots and lots of reaction. It becomes a uncontrolled reaction. And that's not good. That's pretty much a bomb. You do not want that. And they're very serious problems, right? It can cause a thing called a meltdown. The uranium metal itself can literally melt and fall into the water. And when it falls in the water, it's so hot, it causes so much steam in such a short amount of time that it explodes the steam. So an example of that would be Chernobyl. That's exactly what happened. The reactor melted down and that melted metal hit the water and caused a steam explosion. So here's a diagram. If you can follow the flow, you'll be okay. We'll talk about this more later, but pretty much we have the reactor over here, and the reactor is going to be used to generate lots of heat. And you see this pipe here. It is the steel pipe that goes and keeps the water contained. So this has contact with all the radioactive material, and we don't want that to get into the air. So it's always contained and then pumped through its own individual circuit. Now we're going to use the superheated water from the circuit to heat up water over here. As we heat up the water here, it turns into steam, as that red and blue color is indicating to us, and the steam is going to spin the turbine. After it passes through the turbine, it's going to come to yet another set of pipes, and this one is connected to the actual cooling apparatus. So not only does this water never go outside, neither does this. It just constantly keeps getting reused and reused. This water right here, which comes from something like a river or a lake, is what eventually is used to cool both these sets of waters down and then evaporated through the cooling tower, which is this right here. All the while producing lots and lots of energy from our generator, which can be passed down to consumers like us so we can take benefit of that. Like right now, we're using electricity to watch this video to make this video. So comparing nuclear power plants with coal power plants. So for the same amount of electrical generation of 1,000 megawatts, we're going to look at 1 year's worth of data, right? So for 1 year's at 1,000 megawatt coal power plant, you're gonna need 2 to 3 million tons of coal, not 2 to 3 million pounds of coal, 2 to 3 million tons. So 2 to 3 times 2,000 pounds of coal. It's a lot of coal. And as we learned last chapter, most of that is going to be coming from something like strip mining, which is very destructive to the environment. It leaves the soil uncovered, it causes dust particulates, it doesn't look pretty in the ground, and it can cause erosion, all things like that. right? Now, 30 tons of enriched uranium is needed to power the power plant for a nuclear power plant for a year. So not 2 to 3 million tons, just 30 tons. And that's still a lot, don't get me wrong, but it's nothing compared to 2 to 3 million tons, right? So it's much less destructive than coal mining. You don't have the strip mine because we're not looking for mass quantities. You can dig in a localized area and get it. But 1 pound of the nuclear material can release the same amount as 50 tons of coal. So think about that for a second. So what is that, like 100 or 1,000,000 pounds of coal is making the same amount of energy as 1 pound of the enriched uranium. That's pretty incredible, especially when we consider that the uranium will sometimes make plutonium, which we can then use again in the reactor to make even more energy. So the ratio is even less. And as far as carbon dioxide emissions, 7 million tons of carbon dioxide from the coal power plant, but we don't get any from the nuclear power plant itself. But remember, we have to consider how we got to the fuel too. So it did take lots of mining vessels and people and cars and water and everything like that. So it's not perfectly clean, but it uses far less or generates far less carbon dioxide emissions than the coal power plant. And here's a picture of a coal power plant and the ash it produces. So this has always been kind of like a scary picture. It looks like a wasteland to me, and then you just have the big old billowing pumps in the background. So nuclear power plants don't have any of that. So that's good, yeah. Now, sulfur dioxide is another reactant product that comes out from coal mining. So when we're burning the coal, sulfur dioxide can be released. Now, a lot of that is caught by filters. It's not like we're just sending this stuff out into the atmosphere, especially in the United States and other developed countries. But it can get out there despite our best efforts, and it has to go somewhere. The nuclear power plant doesn't produce any of that. All right, it's not a byproduct of nuclear reactions. Last and most surprising would be radioactivity. So we learned this last chapter, but it's good to repeat that the coal power plant, because it's burning radioactive material in the same process as burning the coal, it actually releases way more nuclear radioactivity than the nuclear power plant itself. So it seems counterintuitive, but it makes sense when we kind of start to get like, well, hey, we're not actually trying to release anything into the atmosphere for the nuclear power plant. We don't have to, because we're not making smoke, we're not burning anything, we're doing fission or we're doing fusion. So we're not generating anything like that. Okay, so solid waste, 600,000 tons of ash. You have to bury it in the landfill like we saw. Nuclear power plants, they do create, when they're finished, radiation, and they need to be safely disposed of in concrete tubes and placed underground and in water. So it's not completely waste-free, but 250 tons compared to 600,000 tons is a lot less. Now, there is a special consideration when we're talking about nuclear energy, and that is the fact that if any bad guys got a hold of it, they could use that to make something very, very bad. Right, so if someone got a hold of the spent nuclear material and purposefully exploded that, that's what we call a dirty bomb. And to my knowledge, it hasn't happened yet, but it might. We don't know. So the potential, and we've talked about this before, but the potential for destruction is higher with nuclear, and that can cause a lot of fear of it, understandably so. Now, they're very well protected, pretty well deep in the ground. It's not just they just dump it and they're done with it, but there's always the potential there. Now, the worst case scenario for a coal power plant would be like a fire, like nothing bad is going to happen. But in a nuclear power plant, the worst that can happen is a Chernobyl or Fukushima or outright meltdown that releases a ton of radiation into the atmosphere. So when we're talking about nuclear and coal, one of the main benefits of nuclear is how much energy it produces with the relative low amounts of waste. But on the flip side, and why it gets so much controversy, is because of the potential for danger. Right? There is a much greater potential for destruction if something goes wrong when we're doing this. Not really so with coal. So, in review, what's an isotope? How does it differ from the regular form element? Do you know the difference between fusion and fission? What are the kinds of fuel that nuclear reactors use and how is it gotten? Can you explain three major parts of the nuclear reactor and their roles? How do we generate power from nuclear energy? What is a LOCA in terms of nuclear energy? And how do coal and nuclear power plants